So let's see. So this homework was kind of a disaster. I don't know. It didn't seem like it was, well, the paper was kind of difficult, but the questions were all about the phase diagram. Oops, wrong one there. So in fact, you probably didn't need to read this part. And then it's just this stuff. Let's see. I'll try to do this. Um, see, I don't want this. I don't really get rid of that. Yeah. All right. So that's the questions. And papers like here, and it's just this, like this phase diagram. Right? Anyway, so yes, it's just like trace your way through the phase diagram, right? So you got 0.5 mole fraction. So it's this the red cross, and then slowly cool it to 175. That's like, so this is 150, 175 halfway through. So it's kind of right on that line, right? So if you're up at 350, you cool it down, then you hit the liquidus line, right? And that's going to separate into, so that you can kind of draw a tie line across this from there to there. Then the middle's here. So this amount is the amount of that crystal, which is almost nothing, right? So yeah, wrote down some stuff. You get like a little snowstorm of those crystals at that point. But you're gonna end up with 97% liquid in the end. And so the composition of that liquid is going to be like right here. So in the end, after you cool it down, you get like liquid, and it's going to be from here to there, 97% liquid, like 3% of this little snowstorm of these LiOH crystals. So 3% nothing, basically, kind of comes out. Then you're here, and then you have a tie line between this liquidus and this intermetallic phase, right? So you have those two in equilibria, and you're right at this point. So if you go down there, it's going to be a big amount of the intermetallic and a little amount of the liquid. So you can have liquid domains in the intermetallic, and then the snowstorm thing's over. It's down at the bottom, like the snow's settled. And you just have a matrix of this intermetallic, and then this liquid phase till you get to the eutectic. So that's going to be 40% eutectic. Let's see. Now the composition of the eutectic is 40%, and let's see. And then the composition of that solid, I don't have it here, but it's going to be like, it's kind of almost 50-50 between the two. It's a little bit more of the, I think it's a little bit more of the solids. So you have the liquid phase and the solid. Then that liquid phase is right at the eutectic. It just decomposes, like eutectic decomposition is going to make like a tiger stripe thing. So you're going to have little domains with tiger stripes in them. That's the main thing you have, and the matrix is going to be this intermetallic. There's no two groups are talking about solid solution, but there's no solid solution in here. It's just these things are totally different crystal forms. The LiOH and the LiNO3 and this the gamma whatever Li2OHNO3. They're all different crystal forms. If it was if it was a solid solution, you'd have to have like a two-phase region between them or something. Like it wouldn't be this shape. Like you have a liquid crystal, then you have to have a two-phase connecting. It wouldn't look like this. The phase diagram wouldn't look like this. So anyway, the end result is this kind of tiger skin droplets inside this matrix of this thing. You slow cool this guy. So I'm trying to get you to, it's like a roadmap, you know. I'm just trying to get you to be able to read the roadmap, like how this works, right? So it depends on the rate, but basically it's just like reading a roadmap. Then if you go 300 to 100 rapid quench, so you're at 300 here and you just quench it down to 100. Well, if it's really quenching, you just go to 100 and you just get two phases 50-50 of the LiOH and LiNO3. This intermetallic disappears at 150. You just have those two. So you just do a T jump to here, and it's just makes that and that. It's going to solidify. It's going to solidify 100%, and it's going to make two phases, like the same composition of each. So you're going to, which one is a majority? Doesn't. It'll be just like kind of like grains of both, mixed. So that's what I wanted to get an A. Any comments or anything? Or yes.
So I must have missed it. Why the matrix will be the intermetallic material instead of lithium
material? In the case of like when you do this and over here and then here, because it instead of what?
Instead of lithium nitrate.
Lithium nitrate is like way over here, right? So to come down here and then you're at then you make the eutectic. It's got a mixture. It still has a mixture of LiOH and LiNO3 at this point, right? And you drop down. I mean, these are the minor phase. So it's not going to be lithium nitrate. Is going to be a eutectic mixture of the two. A mixture of actually not of LiOH, but of this intermetallic and the LiNO3. It's a eutectic of those two crystals. And it's going to be mostly the intermetallic, and then so it'll be tiger stripe, but it'll be kind of, I don't know how you'd want to draw it, but basically you're expecting to see tiger stripe, one of the stripes bigger than the other, I guess. Like the LiNO3, Li2OHNO3 would be like bigger stripes than the so you get, I mean, for each of these, you can kind of calculate the amount of each phase, like how, like it's going to be 3% of this kind of powder that comes out of the liquid, and then here, so you can tell like how much by the position, like in the tie line, how much of the two phases and the composition of the two phases, like this is pure, and this one's also pure, right? So for all these, they're like pure. Each one's pure crystal. It's no mixture, but basically you can get the composition of the two phases from the tie line. So there's two things you want to know, like the amount of the phase and the composition of the phase. So if you have two phases, there's 4 numbers you need for each position on the thing, right? That couple, I mean, I'd say the majority of the groups didn't put any numbers down at all, like didn't even bother to like put any numbers down. So it's got to be like, you're reading this to get, because with the numbers, you can say which one's a majority, which one's a minority. So I'm not sure I answered what you asked, but I end up with that it's 20% LiNO3 and 80% of this intermetallic from that. Basically because where it is here. So it's like this is 80%. That's because this is 0.4 and it's only going to half, so that would be
by like lever rule, like how much of,
yeah, so it's 0.4 and it goes to 50, so it's going to be 80% of this guy, of the opposite side, and then it's 10, so it becomes 20% of the other guy, which means that this is a matrix. Those are going to be kind of domains. But this is, it's going to be a eutectic pattern, so it's not going to be like spheres or something. It's going to be like tiger stripe kind of, maybe lines or fibers or something like that. I mean, I think it ends up being something like micelles, where you have like, if one's a big majority over the other, you get spheres, and then as they come closer, you end up with lamellae in the middle, and then there's rods at the side. So there's like lamellae, rods, spheres, and somewhere there's that acicular or something, the fibrous one. So I think it's just kind of like micelles do that too, like when you have the different compositions, and sort of block up on it. So it's kind of, I think that's how things work. It's a geometric issue, like how they fit together. Anyway, so A, B, and C are all kind of the same thing. Like what happens when you do this, what happens when you do that. So it's like 45, so this is the green dot, and then and you're going to rapidly quench it from 250 to 187, and this is 183, 191. So 187 is right in between the two. So you have a liquid solid equilibria in this little teeny spot here. Maybe I can make it larger, but anyway, that region is a equilibrium between a liquid and this intermetallic. There's like a little slice of it when you're above the eutectic. So, and you're right in the middle of that. So, and it's going to be kind of, I mean, it looks like there's going to be more of the liquid than there is of the intermetallic. I think I came up with let's see. I think I'm saying 40%. Let's see, that's a composition of the liquid is going to be this composition, which is, it would be 40%. It's a eutectic, close to eutectic, and then the split is going to be mostly liquid. So it's going to be little domains of this crystal, which will kind of follow the bottom, and then the liquid for that, the first one here. And then what's structure? What would a rapid quench from 250 to 175? So it's the same thing, go to 175. So it's 150, 200, 175 is right in the middle. A rapid quench will just give you the LiNO3 in this intermetallic, and then it's going to be mostly intermetallic with domains of the LiNO3. Right, and as the split's going to be the same. It's going to be let's see, we're at 45, so the split's going to be 20%, I guess. No, 10% of the LiNO3 and 90% of the intermetallic. If you did a quench of that thing directly down, and then 250 to 100, rapid, so just a quench from 250 to 100 way down here, and that's just going to be the LiNO3. It's a 55 to 45 split of LiNO3. So 55% LiNO3 and 45% LiOH. So it's a matrix of LiNO3 with the large domains of LiOH, almost 50-50, but the matrix is that one. So the reasoning is that you're going to get a micrograph of a sample. So how do you make this phase diagram if you just do an experimental? So you make the samples, maybe you do TEM and you do EDEX to figure out the composition of the domains that you see. Then you see, well, one's a matrix, one's not. You can kind of estimate from the 2D what the composition is. And then you can construct this with TEM. I mean, I haven't done that, but that's what you do, and you can see it in papers and things, right? So it's kind of, the reason to do this is that's how you read it, and that's also how you make it. Like if you're going to make these mixtures of these salts, no one's looked at it before, then you're going to do these kind of quenching things and try to find out, to construct this thing, right? So, I mean, if you're doing that kind of work, this is pretty important to know how to do that. Oops. No, escape doesn't work. Oh, just clicking works, I guess. No, clicking didn't work. How did I do that? How do I undo that?
field is quite a constrained areas.
Nope.
Oh.
It's close, I guess, but yeah, all these helpful things. And Mac does the same thing. It's got like these helpful things that you have no idea how to do it. It's like, anyway, so thanks for the help though. But what about rapid? Did I do all these? And then 100 is just a split. So that one, I think a lot of people got that last one, like just you quench it down, you get the split. That's it. So, and then C is same place, 45. By this time you hate 45. And then a slow cooled at 100, the same thing, but slow cool. So what's going to happen here? So you come down to the liquidus and it's going to separate into the intermetallic and it's going to eventually get to be the eutectic. So that's going to be a 50-50 split. So they're kind of mixed, and then this thing separates into the 80%, 20% eutectic structure. So it's going to be domains of that in this thing. Yes. Yeah, so just domains like tiger stripe domains 20% and a matrix of the intermetallic. So anyway, this was not intended to be like, but it ended up being like you guys went nuts on this. So I apologize, but I didn't exactly go through and like spoon feed how to do these things because people that are materials people have already done this stuff and they did a lot of it. And I don't know. Anyway, if you aren't doing this kind of work, you probably don't necessarily need to know how to do this. So, but that's the point of having diagrams. You can pick, I mean, for metallurgy, is you can pick out these structures, right? And for other things, it's just to find the phase separation point usually. It's kind of weird. They're using the eutectic for the same reason that you use an azeotrope in chemical engineering, like to find this low boiling point position, right? So it's kind of funny that they're using the here that way to, and they're also using it, they're claiming that it's a liquid form, right? So then that's like, any other questions on the stuff? Or, I mean, I guess it was too challenging or something, or it's too bad. I don't know, because people just kind of I didn't see any, some people didn't do cartoons at all of the structure. And then some people, so some of the answers were like, there were no numbers at all. Like there's no composition, there's no, this how the split goes between the two phases, what the composition of the phases are, no numbers at all. Maybe just like a descriptive, and then no cartoon of like what it would look like in a micrograph. So the whole point of it is to make a cartoon so you can compare it with a micrograph that you would take, you know. And then in the micrograph, you can go in with EDAX and define like each of the, what the composition of the phases are. Then that you're kind of, if you do that enough, and if you do this, you would be in the microscope for like months. It'd be pitch black. Your eyes would get to be tiny little things, you know. You start to shake a little bit. I mean, it's like, so basically turn into a rat, you know. But you see these guys crawling out of the TEM downstairs. They don't look good, you know. but anyway, that's what they're doing, is like, oh, quench and look, quench and look, quench and look, repeat it, and then like finally, and so you can have much more complicated phase diagram this, and you're trying to find that little divot, this thing in here, like you want to identify that. So you're doing really careful quenches and then a lot of micrographs. So that can be pretty frustrating, I imagine, you know. I mean, they look like they're frustrated. And also to me, yeah, it's interesting, you know. So if you go to probably a metallurgy meeting, you know, and they're going to be talking about this kind of region here, and like there'll be a whole session just on that little region, you know. It's like, especially for nickel super alloys and things, for jet engine turbine blades and things. So there's going to be a lot of little divot things, and people will be arguing whether it exists or not. It's based on they stuck it in the microscope and they saw something. And Gibbs phase rule and a couple other things, but basically you can argue for a long time about that. And as long as people keep paying you, you keep doing it. I think that's what it comes down to. And there's a lot of money in it because it's like defense. It's also like the So jet engines for jet fighters, but also turbines for gas energy production, things like that. So the turbine blades are really important, and that they don't, because when they fail, it's catastrophic. In other words, the plane's taken out. It's the end of the story when one of the turbine blades fails. So the wing is gone, the plane is basically gone. You're at 30,000 feet. So you don't have a really good chance of survival. So they're really, and they're single crystal, usually turbine blades, right? So I mean, anyway, you can see that there's some interest in it, at least in terms of reconstructing crashes or something there. I don't know. Anyway, so the rest of this, so then they make this claim so that you know that it's below 166 and probably below 150, because the polypropylene actually doesn't have a single melting point at 166. It's got this really broad melting region, So 150, it would start to kind of soften and things would fall apart. So you would definitely notice that if it went to 150, the cup would be all distorted, messed up. So it didn't happen. So basically they know it's below 150, yet they claim that this 183 eutectic and the 191, whatever this thing is, those melt, So magically they get to 191, they call it like local heating or something. And then they also mention the water effect. And then you guys brought up this grain thing. I'm not sure it's in the paper. Is that in the paper, the thing about the grain boundaries? Yeah. Okay, I didn't notice that, but yeah, so that was a good thing. So that was pretty good, I mean, that's good. So basically, they come up with all kinds of arguments for why they're sitting at 150, yet the thing's acting like it's 50 degrees hotter, right? And then that's somehow coding these things. So, it's in nature, so it must be right, but it seems kind of weird to me, And anyway, so people commented on that. Some were better than others, and what they said. And then this thing, I think everyone did okay on. It's just the crystal structures, what are they? Just so you know what spinel is and what rock salt crystal is, and and they're talking about it here about the interface, how it modifies the powders. So it wasn't really, the questions weren't really about lithium cathodes, but I wanted to get you some exposure to that kind of field because there's a lot of work going on, like in that area, and you can see the materials part of it's a big part. I mean, so basically, it should be something that you know about. Any comments on that? I mean, like half the people got 50s on this thing, so it was like a kind of a tanked homework. And then there were two groups got like 100. And then I don't know. Was it time constrained? Is something going on like this week, or it's like in the middle of the semester, so maybe it's other exams. Or if you got time constraints, just email me, say like I need more time or whatever. It's okay. And anything else, like I don't really care, like if you turn it in late or whatever. It's nice to have it done before I go through it in class, but I kind of go through it on Friday anyway, or Thursday anyway, so I think it doesn't make much difference. Even if you're just feeling the pressure or something, or just let me know. It doesn't matter to me. Like you can do whatever you want. I just like to kind of get you to learn some of the stuff. And again, this metal phase diagram thing or ceramic phase diagram isn't going to be like ruin your life if you don't know how to do it. There's other things you can do. So I mean, it isn't, but it's a nice thing to know if you're saying material science, because this is one of the main things in material science. So you should probably figure it out at least a little bit. So you could work your way around a phase diagram to get the construction of what it would look like. Anyway, that's that then, if there's no questions on it. All right, so get rid of that. So I want to get this. So this week's homework is kind of like similar to that in that it's a topic. So I'm going to talk about spinel decomposition. This guy's doing artificial intelligence, like machine learning, and also a Nature paper about how to kind of get a little bit about machine learning stuff too. That anyway, so but it's basically about spinodal, which is this kind of structure. You can see the pictures. So it is also something like there's a side subject, but the main thing from this class is a spinodal thing. Hopefully that won't lead to a disaster, like this week was. Trying to wonder, like just stick exactly to the thing, But so anyway, this is called in the book he calls this chapter phase stability. Most part, so he can tack in he can do spinal decomposition, which is kind of a main subject, kind of, but it's more of an academic main subject. But there's a few things like five-core glass is one where you have like that heat, like the chemical glassware that doesn't crack is a spinodal structure. I mean, they leach out the borate, and anyway, so it's that, and then this is these membranes for reverse osmosis membranes are made by spinodal process with polymers. So they do a solvent precipitation. So there's a couple papers on that. Let's see, I think I put them in here. Maybe they're in with the homework. I don't see it here. Anyway, it is in here though. Like the 3M membrane thing. So this thing. Solvent-induced phase separation. So they have processes where they go through spinodal, and then you can get a gradient, porous gradient, like the solvent. So the two phases are polymer and solvent, and then the solvent dries out, and then you get this porous structure you can use for separations, for reverse osmosis. It's on a submicron scale. So anyway, there are a few applications, but for the most part, spinodal is like an academic exercise. I think the guy Kahn and Hilliard were the two guys. One guy was at MIT, one guy was at Caltech. So Kahn, I think, was at Caltech, and I think Hilliard was at MIT, but I'm not sure. Anyway, they developed this theory to describe phase separation in the spinodal region, where you get this uphill diffusion and all this business. Right. So anyway, so that's kind of the idea of this section, is to kind of figure out how that can happen, like how you can get this uphill diffusion to form a web-like structure. Then the homework's a little bit about applications of that. Anyway, I think you guys have seen this kind of thing. So I mean, the idea is like they're showing a gravity in a ball. So that's stable. This is kind of unstable. That's unstable. This is metastable, supposedly. I guess this is spinodal, like you're right on the edge of spontaneous versus non-spontaneous. So if you're on this side, you have to overcome a barrier to do whatever you're going to do, roll the ball. On this side, you don't. It'll just go downhill. Actually, the ball thing isn't exactly the best analogy here. Oh yeah, so the first part of this chapter goes through like superheating, supercooling, right? So we had this, like you had two of these Hildebrand equations, one for the liquid phase, one for the solid. And then if you're going, so you can continue to follow this, like the solid phase over here. So you can be kind of super saturating in the germanium phase, and it would be a liquid if it could reach equilibrium, but it's super saturated. But the idea is like you can reach super saturation at either liquid or solid. And the liquid end, if you go down that road, you're kind of looking at a glass, like forming a glass. The structure will be the same for a glass and a liquid. And then if you're in the solid end, you have a supercooled solid. I'm a superheated solid if there's a temperature instead of composition. So that's kind of the idea. And in fact, they have temperature composition here. So free energy versus temperature. It shows like the liquid free energy. Let's see, free energy's up. So as you heat it up, the liquid, let's see, as you heat it up, the solid, oh, as you cool it down, the solid has a lower free energy. So you get crystallization. You heat it up, the liquid has a lower, right? And there's a melting point where the two are equal. And then at that point, it's possible to cool it down beyond that and get kind of a glass forming. It's possible to heat it up. It's possible to heat up the solid above the melting point, get a superheated solid. Right. So it's something about the kinetics. So kinetics are going to be, so you have like transport of the molecules so that they can reach the crystal site. So it's going to be something like this equation. Right. So you have, if you have, this would be like T naught would be like where the motion stops. So your motion stops at some point other than absolute zero. So you have kind of a Boltzmann equation, right? For the rate of something happening, or an Arrhenius or Irene rate kind of idea. So you have some energy over temperature. But if the thing that's happening, which is transport of the molecules, stops at some point, then you have this T naught, which is called a Vogel temperature, VOGEL. So that's kind of the stopping point. So it could be the TG, but usually it's like below TG, below observed TG, right? And if it's just falling straight Arrhenius, then that's zero. It's like absolute zero. These are in Kelvin, right? So basically that kind of introduces some idea that there's some temperature where this motion, the atomic motions that are important to flow, kind of stop, right? And then this thing, as temperature goes up, the motion gets faster, and then the driving force for the separation, as temperature goes down, it increases because it's a negative free energy ratio for the free energy. So basically, if you multiply those two things together, you find out if you're crystallizing, you have to move things, and you also have like a thermodynamic driving force for the things. Right? And the thermal driving force, as the temperature goes up, gets smaller, and this thing gets larger. So basically, at the large end, at the high temperature end, you get a smaller driving force. At the low temperature end, you get kinetics killing it. So if you look at the rate of crystallization versus temperature, there's a peak in it because you're balancing out the kinetics with the thermodynamics. Right? These are measurements of crystallization of polymers, of polyester, for different compositions, showing that it's got this kind of bell-shaped curve in temperature, which reflects that kind of behavior. And then like the kind of the degree of crystallinity. So this is a rate of crystallization, so it adds up. So you'd integrate that curve to get the amount of crystallinity, right? So that the amount of crystallinity as you heat it would kind of look like that, right? So it's this idea of like kinetics controlling the crystallization. It's more important on bulky, like in other words, this curve on a metal is just a spike. There's no, you don't see the bell shape, it just crystallizes. It's at aluminum or something, boom, done. Right. So you have to have some kind of bulky molecule, maybe like this lithium hydroxide salts. They would have maybe a bell shape to them because they're slower operation. Also, selenium and sulfur form they form kind of chain molecules. Like they'll be like sulfur. Like with proteins, you have a disulfide linkage to lock it together. So sulfur alone will just form a chain. Selenium does that too. Basically, they have kinetics like this also, like there's a broad kind of melting peak, because the kinetics are slow for the thing. Those chains have to weasel around to find the place to crystallize. So you're going to get a broad peak from them. Anyway, so that brings to this idea, this Kautzman, who I don't know who he is. Basically, this is a pretty famous thing, the Kautzman paradox. So you can think about the plot the entropy versus temperature for the liquid and the solid, right? And if you go to the melting point, and if you can make a supercooled liquid, so if you can cool it below the melting point, then it'll lock in, like the structure will lock in, right? But Kautzman came up with this idea, like the liquid always has to have a higher entropy. If entropy is randomness, then the liquid has to be more random than the crystal. I mean, that's kind of a common way to think about it. So, I mean, there's argument, if you read that book on entropy, he'll say like that isn't the case at all, you know. But basically, this is a common way. So if you take that line of reasoning, then you can't cross this line. Like liquid, although it's curving down, can't possibly cross a solid. So you have a paradox that you can't go beyond that. So that's like the Kautzman temperature, and that would be like this T naught thing here. That would be like a Vogel temperature. That was the absolute limit of where you could possibly have a glass transition. So if you cool fast, then you get a glass transition further down. If you cool slowly, it comes up, and if you go infinitely slow, you just get the infinite crystallization temperature, right? So basically the rate of cooling makes a difference in where your TG is. So if you could cool infinitely fast, you'd find this Kautzman temperature. That's the idea of it. So in that idea can be taken. Oh, this is selenium here, I guess. Selenium cooling. So it forms a glass because it's got this chain structure like sulfur does. And then that's all there is. It's in the book, basically. But this Kautzman thing it's in most books. This business, though, isn't in most books. So this is taking the Kautzman thing and taking it another step above, right? So let's see. So he goes through superheating. It's like how far can you heat above the melting point without it turning into a liquid, right? In other words, it's possible to take a solid and then heat it up, and then it'll still remain a solid if it doesn't have some kind of motion that clicks it into liquid. So it can lock in. You can have a superheated solid. It's possible. And the idea is that if you can measure the modulus, so that if the modulus goes to 0, and the modulus decreases with temperature, it's basically if the modulus can go to 0, then this thing can. So what are these moduli here? Right, this is from the book, and he doesn't explain like what these C1112. So this is from continuum mechanics, but so if you have a stress, so you have a tensile stress, you have a force in an area perpendicular to it, and you pull it, right? That's tensile stress. That's a 1-1 stress because a normal to the area is going the same direction as a force. And then the strain is a 1-1 strain because you have the deformation, the change in length is going in the same direction as the change in length. So it's 1-1. In other words, you're taking the change in 1 over the length of 1 to get that strain, right? So that would be like the modulus, the tensile modulus be the C1111 because you have the 1-1 stress and the 1-1 strain, right? So that's kind of the idea here. So you find out that the matrix, so that means that you can have, and there's 3 dimensions. So that means you have like, you have a huge number of moduli, I forget how many, 64 or something. But the matrix is a symmetric matrix. You have half of that, which is 32. And then some of them are 0. And then some of them are 0. So basically, you end up with 16 of these C11, 1, 2, 4, 4. So that this doesn't go along with, these numbers all go with like 1, 2, 3 for X, Y, Z, right? 2, 3, 2, 3. So this would be the shear modulus, right? Because you'd have the shear stress would be like the force going that way, and the areas like the normal to the areas. So it's like a deck of cards. You push the top card with force, and the area is normal to that. So that's like 2 different numbers, 2, 3. Could be 1, 2, 2, 3 is the same. And then the strain is that you're changing the length of it in the kind of X direction, and that length change is varying going in the Y direction. Because a deck of cards, you're looking at how it slides. So you're moving it that way, but the amount of sliding is different at the bottom and the top of the cards. The bottom card's not moving, the top one is. So that's also a 2-3. So 2-3-2-3 is a shear stress, shear modulus. So C4-4 is a shear modulus. And then C1-2 is how, if you do a tensile and then it affects in the other direction. So that's like the Poisson ratio, pretty much. So you're taking like the tensile modulus minus the Poisson ratio, and then this is the shear modulus. They both go to 0 at some temperature, and that would be the instability limit where you couldn't have a superheated solid beyond that point. So this looks a lot like the Kautzmann paradox, but it's for superheated solids instead of supercooled liquids or glasses. Right, so I haven't seen this before, but he puts this in the book. It's interesting that they do that. This C11, C22 thing is in the homework too. Let's see. I can get back over there. So there's let's see. So we got this continuum mechanics thing. This explains it. This is from MIT somewhere, I think. But anyway, actually, I didn't say where it's from, but it's from some class. It's just a continuum mechanics class. You can see he's got the CIJKL, sigma ij strain KL. That's where you get this, all the moduli. He probably says how many of them there are. And then eventually it gets to like, it's a symmetric matrix. And then some of these things have no value. So you end up with only, I think, 16. So some are 0. You end up with 16 of these weird things. And then you redefine the nomenclature so that those things like C11 is that, C12, C13. He's got them all listed here. I think one of the questions in the homework is like, what is the C whatever? Right, so like the normal, this is the normal shear modulus C66, but the others where they're mixed numbers are also shear moduli, just from different directions. Right, because in our paper, he's making a bone implant. So, and he's making a spinal structure with a gradient in it. And if you want to know the mechanical properties in a bone that you stick in your leg, and it's going to be twisted and everything, you need to know all the moduli, not just the shear modulus. Right. So in order to predict the properties, you need all of them. So, right, it's a pretty boring subject, this modulus thing. You know, it's absolutely the most boring subject. I used to have a class when I was in grad school, continuum mechanics. It was at 8 in the morning. And I used to sit in the front row because I didn't want to fall asleep, but I would always fall asleep. Like, and the guy would, maybe I do this too, but he would drone on and on and on. Like by like half an hour into it, and I hadn't gotten enough sleep, just like boom, I'm asleep on the desk. But the guy afterwards, the guy was really nice to me, but it was kind of funny, but I'm not sure he even noticed, I guess. But all right, so anyway, that's that business. Then this thing, what's the other part of this? So, this just all right. So that's the free energy from this, like DG's SDT VDP, right? So negative S. Then if you want to say, when you have the phase diagram, when you have wherever that picture was, I don't have it here. Skip ahead here. So we have this. So this is the free energy versus composition, and then if you take the first derivative of 0 is the equilibrium points. Those 2 points end up being 2 points here, or 2 points on the binodal line, the solid line. And then the second derivative of 0 is the inflection point. So it's this point. So that's the spinodal points. Those end up being the dashed line here. And then the third derivative of 0 is the top. So at this point, the second, third, and first derivatives are all 0, and that's the critical point. So that's actually where this thing goes flat, the whole curve goes flat. So anyway, these derivatives of the free energy are like the key thing. And then to define like stability. So you have second derivative of free energy with respect to pressure. The constant temperature is going to be dV dP at constant T, which is that's the isothermal compressibility kappa T divided by V would be kappa T. And then the second derivative of the so this is defining the spinodal with temperature. It's going to be ds dt at constant P, which is the heat capacity, divided by T. Right. So if you have those two conditions for the spinodal, and then spinodal is the limit of metastability, and if you go within that, so that has to be less than zero, and that has to be less than zero. Then you can define this. Then you can define basically from that you can get that the modulus should behave that way. That's kind of the idea. And there's a picture of the entropy, but basically, if it has when these things equal zero, that's when this thing goes to zero. When the pressure volume goes to zero, that's when you get that this is greater than zero, and that means you've left the metastable region. That's why they justify this plot. Or you could just say that a solid has to have a modulus. That's another argument you could make. You can make it from this perspective of the definition of the spinodal, or you can just say it has to have a modulus. So I mean that's another way to say it. But anyway, so superheating, supercooling is part of the idea of this chapter, which is supposed to be phase stability. So then there's this idea. So we had this thing that you have, so thermal fluctuations, right? Look kind of like this. This is also on there's a motion of this on the wiki page or something. I think I got this from Wikipedia. No, this isn't it. Well, it's here somewhere. Fluctuations. Yes, that picture. Do this. So that's kind of what temperature looks like, or even the composition looks like. I mean, if you can think about it dynamically, so you can see like it's always probing different compositions, and the temperatures, different temperatures everywhere all the time. I mean, this is the argument he was trying to make in that last paper, that it could reach 190 centigrade because of this picture. But I don't think that's really a very good argument. You know, this picture is good to give you an idea of what temperature looks like how you should be thinking about temperature and composition, but I don't think it's a good argument to make that's going to mean that you're going to melt this stuff and that's going to coat a surface. Something seems wrong about that to me, but anyway, so yeah, so this is a slice of that thing, just showing kind of so the reason to show you this is that when you go into a metastable region, and then these regions are just going to grow. So you're going to have this kind of, so this is a spinodal structure that you're looking at. Those fluctuations are the initial stages of spinodal. And you'll see in the homework, he takes a random composition fluctuation as a starting point of his simulation. It just grows from that, right? So that's kind of like the basis of it. And you can see this thing has what they call a bicontinuous structure. So if you start here and you're in blue, you can drive all the way through it to some other place. So that's a tunnel that goes all the way through, and the tunnel's about the same width. So the phase size is about the same. And also, if you're in the clear part, you can go from one side to the other in the clear part also, right? So that means bicontinuous. That's one of the features of spinodal. The other is that there's a constant mean curvature to this thing. So let's see, I don't remember exactly how to define that, but it means it looks like this. Like it's got a smooth curvature to the structure. There's something about the radius of curvature. I don't remember exactly the definition of constant mean curvature, but it looks like this. Basically, it's got this kind of, it's a mathematical thing for a structure like this. There's a couple other things about spinodal. Actually, they're listed on the homework, but so let me just look at that for a second. I listed all of them somewhere here yesterday, but homework 6. They're all listed here somewhere. Stochastic, so it has to be kind of random looking. And it has to have periodic domains of narrow. So periodic domains means that this thing, so the spacing between these domains, even though they're random, is fixed, kind of fixed, right? So even though, so this is a periodic structure, a periodic stochastic structure. It's random and it's got a fixed distance between things. So if you know, you can get diffraction from this because of the fixed distance. When you have a fixed distance, the transform of that is kind of a spike in a diffraction pattern. So the Fourier transform of that kind of correlation function is a spike. So you get a peak, even though the thing looks like it's completely random. So that would be a signature. The correlation function should have a hump in it. Right, and then what else? Interfacial concentration gradient should go against fixed law. In other words, you're not diffusing from the high concentration to the low, you're diffusing from the low to the high. The reverse diffusion interfacial gradients. And then that's it, I guess. That's the list I got. That's basically what I have for spinola. That's what it kind of looks like. And in that paper, like they're doing machine learning. So basically all they're doing is what it looks like. It's a game of what it looks like. It isn't a game of understanding how it forms or anything else. So machine learning means you take a picture of it, and then your computer, if you take enough pictures of it and you feed those into the computer, it can reproduce that picture, something close to that picture. It's like they can reproduce humans and things, right? Pictures of humans and whatever. So it's the same idea, except in 3D. And it's not a human, it's some kind of weird thing, weird network thing. But all right, so anyway, this is how I'm just following along the chapter, but with a few things added. Like he doesn't, I think, talk about cyclohexane, but this is, so cyclohexane, when you reach a certain temperature, like 1,000, so cyclohexane is a 6-membered ring. It's like benzene, but it's not aromatic, so it doesn't have double bonds in it. So benzene's a planar molecule, like a double bond, a conjugated double bond, single bond, double bond is flat. It's totally flat, right? So it's a sheet. So this isn't a sheet because it doesn't have double bonds. So in each of the carbons is tetrahedral, it's got 2 hydrogens sticking out from each one of them, right? So they kind of get in the way. And because of that, it has a torsion. So it has to form this kind of bent thing, right? That looks kind of like either a chair, or if you flip, it's a boat like this, right? So anyway, when it's a boat, these 2 ends are, you can think of hydrogens sticking out, the 2 hydrogens are kind of near each other. So that's not good. So that when it's para like this, the hydrogens are away from each other. So that means that's better. That's a lower energy. So because sterically the hydrogens hit each other, this is a higher energy, that's a lower energy, right? And temperature is going to be 2.5 on this scale. This is KT, would be like 2.5. So normally we're surviving kind of down here, and almost everything is in a chair form, this molecule. But if you go like the energy difference between that chair and that boat divided by KT, you can find that if you go to 1073 Kelvin, you get 30% boat and 70% chair. So it flips out because you can, at that temperature, you can kind of climb over the barrier and form more boats. So if the temperature is up here, then it's going to be like an even swap between boats and chairs. But in order to flip between them, it has to go through this transition state. So you have a stable state, transition state, and then this metastable state, and then these stable, kind of the stable states. Metastable states, and then there's two kinds of boats. It can flip. So to flip between that, it has to go through this twisting action. And there's a terrible twisting, and there's just a twisting between the 2 kinds of boat things, or 2 chair things, whatever. Anyway, the energy diagram looks like this. They know that because you can tag these hydrogens, and you can measure the distance between the hydrogens with NMR. The peaks of the NMR split when the hydrogens interact with each other. So you can know from the position of those peaks of the NMR, the splittings, how close all these hydrogens are to each other. And from that, you can reconstruct what the atom is. And you can do the NMR at different temperatures, and you can see kind of how this thing works. So you can, from the NMR measurements of the structure, you can figure out, and the temperature that they were taken at, you can figure out like all the energy, you can figure out this entire energy map. Right? So that's how you kind of get this thing. Right? So anyway, so cyclohexane is like a popular item for this kind of map, to look at energy diagrams. And the idea of metastable and stable states and transition states. Anyway, so anyway, let's see, what is this about? I don't remember. Shared a boat. It's just saying that this can be concave up, concave down. I mean, we said that already, like kind of the smiley one is a stable phase because anything goes uphill. And then the frown one is unstable because anything's downhill. So any change would drop the free energy if it's kind of a frown, and any change would increase the free energy if it's a smile. That's the idea. So it stays where it is if it's a smile. So this is from the book also. So he's talking about let's see. He defines this affinity. So if you're going to change from state A to state B, I guess, so this would be like chair boat, or it could be two different phases, like A and B transition is a chair boat transition. So if you make more boats, then you're going to have to get rid of some of the chairs. So DNB has to be negative DNA, and that becomes this kind of reaction coordinate, just the change, whether it's a boat or chair is a reaction coordinate. And then the change in free energies is kind of the chemical potential of the chair, chemical potential of the boat. So in other words, if you add one more boat, does the free energy change? How much free energy does it change when you add one more boat to the system? That would be the boat chemical potential. And then if you want to write this out, so because the boats and chairs swap out, then it has to be the difference between the two chemical potentials times this reaction coordinate gives you this free energy change. So that defines this term, the difference in chemical potentials, is this affinity, the affinity for chair or boat. So the reason to say that is because then you can, once you have affinity, you can write it in a Taylor series in the reaction coordinate, and then you can just start defining things in terms of this. Sorry, I got kind of, the guy was for the next class canceled out, so I had to kind of figure out stuff before this class for the other thing. And then I kind of didn't get to go through these notes before. I'm losing track of what's going on with this thing. Like, anyway, let me just see what's going on. Oh, this is just trying to calculate the critical points and using the Hildebrand equation. All right. So the affinity, I'm not sure why I have the affinity here. I think this is just from the book, so I put it in. The point is actually to get this, to calculate, use the Hildebrand equation. So if you have the Hildebrand, you have the actual free energy, and so you don't know the actual free energy, it's only relative to some standard state. So you take like the composition times the chemical potential of the standard state. So this is just delta G. Gm minus that would be like delta G. And then this is the equation we had before. So basically, if you want to know the binodal, you take the first derivative. So you take the derivative with respect to xb. So this will be ln xb, and then the derivative of ln xb is dxb over xb, so that cancels out. So it's ln xb plus 1, right? And then the derivative of 1 minus xb is minus ln xa. So you have ln xb minus ln xa. And derivative of ln xa is derivative of xa over xa, so that's plus 1. That's minus 1. So you have minus 1 and plus 1 cancel out, and you end up that the derivative of this term is just that xb minus ln xa. Then this thing, so derivative of xb is xa. I mean, take the derivative, it's just going to be gamma xa for the xb derivative. This will be 1 minus xb, so minus xb dxb. For this term, so you end up with 2 xb's and a 1 from 1 gamma. Anyway, you end up with this expression from the derivative of that. That will come right out. If you use like xa is 1 of xb and d ln xa is dx over x. So if you set that equal to 0, you can solve it, and then you can find out what the binodal composition is in terms of the Hildebrand parameter. Right, because there's just the composition. Xa is 1 minus xb, so just one composition here and one Hildebrand parameter. So just that term defines the composition for the binodal. And then the spinodal would be the second derivative of that. So you have to take the derivative of this thing. So again, like derivative ln xb is dxb over xb. So you have 1 over xb, and derivative of this is 1 minus xb. So it's going to be the negative comes in. So you end up with 1 over 1 minus xb, which would be 1 over xa. So that, and this thing doesn't have, or this thing, only the 2 gamma ends up, negative 2 gamma. So that's the second derivative, set that to 0. Then you can find the spinodal. Same way. So you have xa xb is RT over 2 gamma to get the spinodal. Then the third derivative is find the critical point. You do the derivative of like this equation. That ends up giving you this, and that you can solve for 50%. That just gives you that the critical point's at the center. And then you can plug, then let's see, actually to get that 50%, you have to, because all three, this, that, and that are all equal to 0 at the critical point. So you can, you have to use 2 of these to solve for the critical point, I think. That's why I remember it, but yeah, because you have, let's see, you have T. Yeah, I think you have to, no, you divide by RT, then you just have that thing, and that only works with 50%. So I guess you only need that to get the critical point. Anyway, so if you plug in the critical point back into this equation, the 50%, then you can find out what the critical temperature is, because that is equal to 0. We plug in 50%, you can find out the critical temperature is gamma over 2R. Right, so you can solve the entire spinodal, binodal, and critical point just by doing derivatives of the Hildebrand equation. So that's kind of the idea. And then you can construct these things using the Hildebrand equation just by doing derivatives of that. So they're all temperature dependent. So you just plot out the temperature dependence of each of the spinodal, binodal, critical point. And that's for the, so you can do the same thing for the Flory-Huggins equations, exactly the same approach, and you can predict the phase behavior. So we already went through this thing, through that. So anyway, if you phase separate in this middle part, so if you do a quench into the spinodal region in the middle, then you end up with this kind of web structure, like this thing, right? And if you phase separate into the binodal part over here, that's metastable. You need a nucleus to initiate the phase separation. You end up with this kind of spotty phase behavior, little domains like nuclei grow. This thing spontaneously forms. This needs to have nuclei. In other words, in this case, you can get a supercooled liquid. Like you can have it a single phase, even though it's within the binodal, if it's perfectly clean with no dust. Whereas this won't form. This will automatically form without dust, like when you quench into that region. Right. So that's the idea. Like the spindle will just spontaneously form. So, and then I mean, I guess it was noticed early on that there's a spacing to it, and somebody had the idea like the transport has something to do with that spacing, and then it also has to do with the thermodynamics of the what's driving the phase separation. So that more or less led to the kind of development of Cahn-Hilliard theory. But so anyway, so this what happens with time though is that the thing coarsens. This is called coarsening and Ostwald ripening. So basically the domains grow with time as you're in the spinodal region. So it isn't a fixed structure. The structure coarsens. So basically with time, it'll eventually look like nucleation growth if you wait long enough. It'll end up being just domains. Right. So so if you shoot a beam of light, if it's a polymer, these are on micron scale. If you shoot a beam of light with a micron wavelength, you get this ring. So that's the signature of spinodal decomposition. You have a ring because the structure is random, so it has to be symmetric, but there is like a kind of a diffraction peak to it, right? And this is just showing like if you wait early stages, it's just following at the same position, the ring. But if you wait long enough, the ring collapses. So there's an inverse relationship between the angle which is going out. So in other words, a beam of light comes through, passes through the sample, and then this is like a photographic film that's a picture's taken on it. But as time goes on, the ring collapses because things get larger. So it's basically by Bragg's law, the smaller the angle that you're measuring at, the larger the size. So the thing is, this collapses down to the middle, you're getting larger and larger size domains, which corresponds with this kind of picture that the things coarsen with time. Right, it's because of they want to reduce the surface area. Anyway, so that's a picture of the fluctuations. I think I drew that before. So the spinodal's spontaneously forming and nucleation growth. Because you have a phase formed, it depletes the concentration next to the phase, so that you have downhill diffusion. Because when the phase forms, it's in a different phase. It's consumed the material next to it, and that drives in. Whereas in spinodal, there's nothing like that happening. It just things are just spontaneously decomposing, right? So that it's an uphill diffusion going on. So anyway, let's see. Yeah, this is just showing how we'll talk about this more later on. But if you say you're making a nucleation growth regime and you're making a phase, right? So it's got a volume, like R cubed is a volume, then it's got the free energy of that phase forming, the difference between the phase forming and not forming. And then once the phase forms, it's got a surface, and this penalty is a surface energy. So R squared times the surface energy, right? So if you can set this to 0, then you get a size out of it because it's squared and cubed. If you divide by squared, you get a size. So that's like a magic size. There's some kind of critical size that happens because of the balance between the surface energy and the bulk energy. Right. So that kind of decides this peak size that occurs. And if you go to larger sizes, let's see. Oh, this is positive, that's negative. That's the issue. So as you get to larger sizes, you get more reduction in the free energy. So the thing that drives the growth of the phase. Right? So and this stops the growth of smaller phases. So it depletes at smaller sizes. Anyway, so basically, yeah, this nucleation rate is going on, and also this growth phenomenon is going on. Those things kind of balance out, I guess. That's kind of what's going on here. So anyway, this is mostly this chat. We'll talk about that more when we do surfaces. Like we'll go through this at length and surfaces. But basically, I just stuffed that in there because that has to do with the nucleation growth part of the curve. The spinodal part, though, this is from this paper by this Taki Hashimoto. Is kind of like the father of polymers in Japan, more or less, but he did quite a bit of work on spinodal decomposition. I think this was one of his first, like 82 is one of the first papers he did on it. And this is the same, like if you look in the paper for this week, it's like almost the same. And every spinodal paper has almost the same stuff in it. But I think this is maybe a little bit easier to read. So yeah, this is the like the free energy. And there's this thing called a free energy density function. So that's like that's basically our Hildebrand equation, right? And there's this gradient term. It's like the penalty that it costs to have a concentration gradient. And then kappa is a prefactor, like a penalty for that concentration gradient. So the free energy is going to be an integral over all the volume elements in the system of the free energy of the composition there and the gradient there. Right. So somehow you can write an expression for the free energy that includes this gradient term. Sorry, fixed law gives you this idea like the changing concentration with time is going to be the second derivative of the free energy times the diffusion coefficient times this gradient term. So you can do it's like a power series and this concentration gradient term, and then this differential equation can be solved with an exponential, and the exponential is this growth rate of the phases. So this is saying that, so this is kind of a sine wave. So basically the phases in the spinal decomposition are going to be like sine waves. And it's going to be like the wave vector times the positional gives you the frequency of the sine wave. And then this is the rate of growth at that size scale, at that wave vector. So the growth rate, this growth rate is going to be related back to the free energy expression. It's going to be basically, by doing the derivative of this and comparing it with that, you can get what the growth rate is in terms of this free energy expression. So free energy expression is the Hildebrand equation. So you take the second derivative of that, you can get the growth rate of the spinodal phases. And then you have this kappa term has to do with the interfacial penalty of it. So anyway, you can measure these things. So basically the growth rate, the RQ means like you measure the intensity as a function of time. So time's going up and the peak intensity is growing here. If you measure the peak intensity versus time, if you do log linear in time, it follows that equation. And then basically you can get from that the slope of that is growth rate, the R of Q, and from the R of Q, if you relate it back to the Hildebrand equation, then you can predict what R of Q is from the Hildebrand equation. And then you can basically the interaction parameter and the composition will give you like how fast that spinal decomposition is going to happen in the system. The kappa, so it's a balance between the thermodynamics and the transport properties lead to the growth rate of the phase at some value of this Q. So this function, so you can do, so it's got to be a linear function of intensity and time gives the growth rate. And if you look at the growth rate, and you can do plots of the growth rate by taking the derivative of the in this case, the Flory-Huggins would basically be the same with the Hildebrand. So you'd have like omega minus spinodal omega. Spinodal omega you can calculate from the second derivative, right? So spinodal omega is just going to have the temperature in it, the spinodal temperature. So anyway, so you can from that you can calculate the growth rate from the transport and the thermodynamics of the system, and this is a kind of an entropy of the gradient, they call it, and it has to do with just the size of the molecules in the system. So anyway, so that's kind of yeah, there's not an easy way to go through this stuff, I think. In short, you can predict from the Cahn-Hilliard theory, you can predict every feature of the structure that's coming out of this thing. And it works, so that people were pretty happy with this theory. And it's based on just the idea that you can take the free energy and the transport, and couple them together and just come up with basically a size that grows out of the system. That's more or less the idea of it. So anyway, let's see what else we have in here. We don't need to go through that. Yeah, so anyway, there's some examples of spinodal. So like Vicor, so this is for borated silica glass, right? So you have like Vicor and Pyrex, right? So Pyrex is made in nucleation and growth regime. So you have, so the borate phase is in the silica still. So it ends up being like turbid, kind of, right? Whereas Vicor is grown in the spinodal, and then you leach out the borate phase, and that gives you and then you quench it down and you make a clear glass with it. It's just like the spinodal one's like clear glassware this won't crack when you change the temperature, and the Pyrex is kind of tough, like it won't break, but it's still got borate in it because there's not a co-continuous phase. So you can't leach out the borate. The borate dissolves in water, so you can get that out of the Vicor one, but not the Pyrex one. So that's like one of the main examples of spinodal is Vicor glass. And then what else is in here? I don't remember what this is. Oh, this is just showing like how you, so it's just showing that you can get because the critical point is going to be the third derivative of the free energy, wherever that is. This actually belongs earlier. So you have the critical point's the third derivative, and you can you can look up the critical temperature, pressure, and density, like that's tabulated. So that means that if you have a free energy expression, it's not clear why this is here in this chapter, but it is. So if you have a free energy expression like a van der Waals equation, like an equation of state, then you can take derivatives of it. If you can get the third derivative, then you can say that the third derivative is set to 0. In fact, all the derivatives are 0 at TC and PC, right? So if you start taking the derivatives of this, like P versus V, first, second, set them to 0, and then plug in the values, and you can solve, because if you have two equations and two unknowns, A and B, you can solve those for the TC, PC. So basically then, if you know the critical parameters, you can look up in a table, they can predict what the A and B van der Waals parameters are. And then you can just, in fact, you can rewrite the whole equation just in terms of P divided by PC and V over VC, and then get a universal equation of state, right? So basically, this idea of using the critical point, because you know the numbers for the critical point, it's a single point, and it's tabulated, then you can predict the whole equation of state for simple molecules where you have a critical condition. That's that business. I'm not sure why that's even in here. Yeah, the last part of the chapter just talks about, it's kind of like a mixture of things in this chapter, actually. But the last part just talks about polymorphs and just that they exist, basically. And then Oswald ripening. But so why don't we quit there for today? You know, sorry I'm disjointed today, but it's kind of how it goes. I guess because this other class got messed up. So hopefully that's all right. next time I'll go through the homework, for the weekend, but.